Hello, good morning. Myself, Dr. C.J. Kadam, Head, Department of Physics, Maharashtra Mahavidyalaya, Niranga, Latur District, Maharashtra. Today we are going to discuss electromagnetic induction. Electromagnetic induction. Oersted experimentally proved that as the current is passing through a conductor, it produces magnetic field surrounding the region. This is called as magnetic effect of electric current. On the other hand, Michael Faraday discovered the inverse effect, that as there is a change in the magnetic field, it produces the electric current in the circuit. This phenomenon of the changes in the magnetic flux linked with the coil, as there is a changes in the magnetic flux, we will find that the current is produced in the coil. This phenomenon is called as electromagnetic induction. Okay, the total number of lines of induction over a given surface. Okay, if it is represented by phi, and the magnetic induction, if it is P, the magnetic flux, the total number of lines of induction is called as the magnetic flux phi and is measured in Webers. Okay, so that if the magnetic induction is represented by B for a coil of area A with number of turns N, so that this phi is given by phi is equal to N into AB. If this magnetic induction B makes an angle theta with the given surface, so that this is given by phi is given by NAB cos theta. The SI unit of this phi is Webers and the scissors unit is Maxwell. Now we shall see the Faraday's experiments. First experiment we will say that the coil and magnet experiment. We shall see the coil and magnet experiment to explain the electromagnetic induction. Okay, so we have a bar magnet which is placed near to a coil connected to a sensitive galvanometer. Okay, now this experiment consists of a coil. The two terminals of the coil is to be connected to the sensitive galvanometer and a bar magnet is placed near to the coil. Now, as this magnet is moved towards the coil, we will find the deflection in the galvanometer. That is, the current is set up in this circuit. If suppose the bar magnet is moved, instead of moving towards the coil, if it is moved away from the circuit, so that we will find the deflection in the galvanometer, but it is in the opposite direction as that of the first one. If this bar magnet is kept stationary, we will not find any type of deflection in the galvanometer. So that the deflection in the galvanometer is obtained only when if there is a relative motion between the magnet and the coil. If it is moved towards the coil, we will find the deflection in the galvanometer in the sense induced EMF is to be developed in the coil. And the induced current is to be developed, so that we are getting deflection to one side. Now if the magnet is moved away from the coil, we will find again deflection in the coil, in the galvanometer, but it is in the opposite direction. Now if you want to increase the induced current which is to be produced in the coil, so that we have to either increase the number of turns of the coil so that the induced current in the coil will be increased, or you have to the speed of this relative motion is to be increased so that we will get the increased induced current in the coil, or you have to use the third one as a high strength magnet. Okay, if you want to increase the induced current in the coil, we have to consider three cases. Either the bar magnet is to be used of the high strength, greater strength, or the speed, the relative speed between the coil and the magnet is to be increased, or the number of turns of the coil have to be increased. Okay, so if you increase the number of turns, we will get the increased induced current. If you change the relative speed, if you increase the relative speed between the magnet and coil, we will get the increased induced current. So this is one of the experiments called as Faraday's experiment, called as coil and magnet experiment, by means of which we are getting the deflection in the galvanometer by its relative motion towards the coil and away from the coil. Now we shall see the magnet coil experiment, Faraday's experiments. Now we shall see the Faraday's experiments. The coil and magnet experiment. So we are using a bar magnet having an NS poles, and here is a coil. The two terminals of this one are to be connected to the sensitive galvanometer. Okay, the two terminals of this coil is to be connected to the sensitive galvanometer. This is the coil and magnet experiment. Now we are going to say something about the Faraday's experiments. We are going to discuss something about the Faraday's law then after explaining the Faraday's experiments. The first experiment is that coil and magnet experiment. So in this coil and magnet experiment, we have a bar magnet and a coil, and that the two terminals of that coil are to be attached to the sensitive galvanometer. If there is a relative motion between this coil and magnet is there, then only we will find the deflection in the galvanometer. And if there is no any relative motion between the bar magnet and the coil, we will not find any type of the deflection in the galvanometer. Now suppose that if we move this magnet towards the coil, so that we will find that the deflection in the galvanometer, that means that the current is set up in the coil. On the other hand, now if we move this bar magnet away from the, okay, initially we have moved the magnet towards the coil so that we found deflection to one side. Now as we move this bar magnet away from the coil, so we will find that deflection in the galvanometer, that is in the opposite side as that of the first. In this sense, again the current is set up in the coil. Okay, now as with this we say that as there is a relative motion between the magnet and the coil is there, then only we are getting the deflection in the galvanometer. The current is set up in the coil. Okay, so that if we now move this magnet facing the north pole towards the coil, so that the galvanometer shows reflection, and now this coil will act as a dipole, showing its the face towards the magnet as a N pole. Okay, and so that the induced EMF is to be set up in the coil and the induced current is set up in the coil. Now we will find deflection to the one side. Now on the other hand, if we just move this magnet and keep this magnet in such a way, bring this magnet near this coil in such a way facing its south pole towards the coil instead of north pole now. Okay, so if the poles are to be interchanged, this is north and this is south, facing the south pole towards this one, so that now again we will get the deflection in the galvanometer, but in the opposite direction. And this coil now acts as again dipole, such that the face of this coil will act as a south pole towards this one, and the galvanometer is giving the deflection. Induced EMF is set up in the coil and induced current is set up in the coil. On this basis, we say that if we move this magnet towards the if we move this magnet, if there is a relative motion between the magnet and coil is there, then only we will find the induced EMF is set up in the coil. Otherwise, no. On the other hand, we can just keep this magnet fixed one. The coil is also moved away from this magnet, and coil is moved towards the magnet. We will get deflections in the galvanometer. If we move this coil towards the magnet, we will get deflection to one side. On the other hand, if we move this coil away from the magnet, we will get the deflection in the galvanometer, but in opposite direction as that of the first one. If both are kept stationary, we will not find any type of deflection in the galvanometer. Now, if we want to increase the induced current in the coil, so that we have to do that the number of turns of the coils have to be increased, so that we will get induced EMF to be increased one. On the other hand, if we use the high strength, greater strength magnet, so that also you will get the induced current to be increased one. Okay, so the number of turns are to be increased, you will get the increased current. On the other hand, if we make use of this high strength magnet, also you can increase the induced current, or the relative speed of this magnet from the coil towards the coil or away from the coil is to be increased, so that you will get the increased induced current. The coil and coil experiment. So let us have a coil A which is connected to a cell, and in series with that one a tap key is to be connected. So this is a cell having positive negative, this is tap key of EMF E cell, and this is the coil A. And then the another coil is there which is just kept near to the coil A. This is the coil B, and a very sensitive galvanometer is to be connected to this coil B. Okay, so this is coil and coil experiment. This arrangement shows you the coil and coil experiment. Faraday's experiments we are discussing. So the second experiment we are going to discuss over here, the coil and coil experiment. Okay, so here is a coil A to which we have connected a cell. Okay, and in series to the cell there is a key, and near to this coil A the another coil is to be connected placed, the coil B, and the terminals of the coil B are to be connected to the sensitive galvanometer. Now, if we press this key, okay, if we press this key so that the current starts to flow in the coil A, so that the induced EMF is to be the developed in the coil B and the galvanometer deflection is to be same. As the current increases, okay, as the current increases, we will not find any type of deflection in the galvanometer. If we break this, uh, the tap key is to be released so that the current starts to fall down. As the current is to be stopped in the coil A, we will find again the deflection in the galvanometer across the B coil. The galvanometer which is to be connected across the B coil. Okay. So here, while making the circuit, there is a deflection in the galvanometer, and while breaking the circuit, there is a deflection in the galvanometer, but in opposite signs. As the current is increasing steadily, we will find that the EMF is to be increased continuously, but as there is a further increase, we will not find any type of deflection. As it is to be just decreased or stopped down, the current flowing through the coil 1 is to be stopped down, so that the lines, that is the lines of forces, the flux which is linked to the coil B is decreased, and we will find another the deflection in the galvanometer, but in opposite sense. So the induced EMF is to be developed in the coil B due to the current flowing in the coil A. So this is the coil experiment. So we have seen that the coil and magnet experiment and then the coil and coil experiment. On the basis of these two experiments, Faraday proposed two laws called as Faraday's law of electromagnetic induction. Faraday's laws of electromagnetic induction. So on this basis, on these two experiments, Faraday proposed two laws. The first law is that the statement of the first law is given like this one. Whenever there is a change in the magnetic flux linked with the circuit, the induced EMF is produced. Okay, the first law states that whenever there is a change in the magnetic flux linked with the circuit, there the induced EMF is produced. This is the first law. On the other hand, the second law states that is the flux is to be whenever there is a change in the magnetic flux, the induced EMF is to be produced. Okay, so the second law is that the magnitude of this induced EMF which is to be produced, okay, is directly proportional to the rate of change of the magnetic flux. Okay, this magnitude of this induced EMF which is to be produced in the circuit is directly proportional to the rate of change of the magnetic flux, d phi by dt. If you remove this proportionality sign, so that we take this one as a constant k into d phi by dt. If E is the induced EMF, okay, in this circuit, whereas phi is the magnetic flux, so that this E is directly proportional to d phi by dt, which is the rate of change of the magnetic flux, so that the proportionality sign is to be going to be, we take a constant. This, as the constant k is equal to unity, so that we get this E is equal to d phi by dt. Okay, so this E is measured in volts, whereas the phi is in Webers. So as to determine the sense of this induced EMF and the sense of the current which is to be produced in the circuit, Lenz proposed a law and is called as the Lenz's law. Okay, so as to know the sense of the induced EMF which is to be produced and the rate of change of the phi and the current which is to be produced in the circuit, Lenz's proposed a law, and that law is called as the Lenz's law. So this law, the statement of this Lenz's law is such that is the induced EMF which is to be produced in the induced EMF which is to be produced in the circuit is such that it opposes the changes of the magnetic flux which produces it. That is, if we combine the second law and the Lenz's law together, we get that this is equal to minus of d phi by dt. This is the Lenz's law. The statement of the Lenz's law is like this. Induced EMF is such that induced EMF which is to be produced because of the changes in the magnetic flux in the circuit is such that it opposes the magnetic flux, changes in the magnetic flux which produces it. That is, here the negative sign says that the EMF is opposing to the changes in the magnetic flux. You can take the example of this one to explain the Lenz's law. Okay, so the coil and magnet experiment to explain the Lenz's law. Now, as we have the magnet which is placed near a coil, the coil is to be connected, the two terminals of the coil is to be connected to the galvanometer. If we place this magnet stationary, if there is no any relative motion with the coil and the magnet, we will not find any type of deflection in the galvanometer. If we move this magnet towards the coil in such a way that the end facing towards the coil, so that here the coil acts as a magnetic dipole in such a way that the face towards the magnet is north, so that induced EMF we are getting the reflection in the galvanometer as it is moved towards the coil, so that the north pole is to be it is giving a north pole, the face towards the bar magnet is north pole, so that the north and north pole will now repel each other. Therefore, the induced EMF which is to be produced in the coil is now opposing the changes. On the other hand, if we just move away this bar magnet from this coil, so that again it is acting as a magnetic dipole in such a way that is the face of the towards the magnet will act as a south pole. We will get again deflection in the coil, but in the opposite direction as that of the first one. Now this south pole and this north pole, now it tries to attract the magnet towards the coil. That is, it opposes the changes. That is the EMF which is to be produced. The deflection which we got in the coil, that is the EMF which is to be produced in the coil, is opposing to the changes in the magnetic flux. So this is about the Lenz's law. Okay. Self-induction, L, represented by L. If you have a circuit containing a coil connected to a cell of strength E and in series with that one a tap key K. Okay, so this is a circuit which consists of a cell of strength E and tap key K and a coil. Now let us see that if the tap key is pressed so that the current starts to increase in the circuit. So that as the current starts to increase, we will find the induced EMF is developed in the circuit. As suddenly we will not find there is an increase in the current. It will take certain time to reach its steady state. As long as the current is changing in the circuit, so that we will find that the EMF which is to be produced in the coil is also changing as it reaches its maximum value. Then onwards, if we close the key, if we just remove the key, the circuit is break, so that we will find that again it will take certain time to collapse down. That the EMF which is to be produced in the coil is also now opposing for the changes. Okay, initially while making the circuit, while developing the current in the circuit, the EMF is continuously increasing. While breaking the circuit, the current is to be decreased so that the EMF is also decreased, but it opposes the changes. Right? So that now what this phenomenon, okay, as there is a production of induced EMF in the circuit because of the changes the current in the same circuit is called as the self-induction, okay, represented by L. If suppose the current flowing through this one is I and the magnetic flux which is to be developed in the coil is phi, say, so that this phi is directly proportional to the I. So if you remove the proportionality sign, so we take a constant, and that constant is totally dependent on the geometrical properties of the coil. Okay, so as per there is a change in the current, so that we will find the changes in the magnetic flux. Okay, so we take this one in the form of, that is, E is equal to, according to the Lenz's law, minus of d phi by dt. So now we will take this value of phi from the equation number 1, so that this is minus of d by dt of Li. So this minus L is to be taken out, so we get di by dt. So if suppose in this circuit the di by dt, rate of change of the current in this circuit, is say 1 ampere per second, so that we will get, if this is equals to 1 ampere per second, so that we get the magnitude of the EMF which is to be produced in the coil is to be equals to L. That is, the L which is to be produced in this circuit is equals to, that is, E upon di by dt, and this is equal to L. From this one, we define that the L is here called as the coefficient of the self-inductance, okay, of the coil. Now, the unit of this one is Henry. Okay, unit of this one is Henry, and represented by H. So we define 1 Henry. Okay, we define 1 Henry, the self-inductance of a coil. The self-induction which is to be in a coil is 1 Henry, that when 1 voltage of EMF is to be induced in the coil, because of the rate of change of current in the same coil is 1 ampere per second. Okay, the self-induction which is to be defined as, it is the production of induced EMF in the coil because of the changes of the current in the same coil, and is given by E is equal to, that is, minus of L di by dt, therefore L is equal to minus of E, okay, minus of E, this is upon di by dt, L is equal to minus of E upon L di by dt. Mutual inductance, mutual induction represented by N. Let us have two coils, so the coil number A and coil number B. the coil number A is to be connected to a battery, and which is to be connected further to a tap key. Okay, this is the coil number A, this is the resistance E, and the coil number B is to be placed very near to the coil number A. This is the coil number B, and is further connected to the sensitive galvanometer. Okay, so now we have here two coils which are placed near to each other, coil A and coil B. Coil A, the terminals of the coil A are to be connected, one terminal is to be connected to the cell, and in series with that one, a tap key K is to be connected, and the coil B is placed near to the coil A. The terminals of the coil B are connected to the sensitive galvanometer. Now let us see that, press this key so that current starts to flow in the coil number A. Now as the current is flowing in the coil A, it induces the EMF is to be induced in the coil B in such a way that the magnetic flux which is developed in the coil B, and so that we will find a deflection in the galvanometer. Okay, so this phenomenon, because of the changes in the current, now the current as it is to be just the key is to be pressed, current starts to increase. It takes certain time to reach its steady value so that we will get the deflection in the galvanometer. On the other hand, if we release the key so that we will find that the current in the coil A is decreasing, so that the induced EMF which is to be developed in the coil B is also decreasing. We will find the deflection in the galvanometer, but in opposite direction. This phenomenon of the induced EMF which is to be developed across the coil B because of the current which are to be changing in the coil number A is called as the mutual induction. Okay, and is represented by N. If suppose phi is the magnetic flux linked with the coil, so that and the current which is flowing through the coil is I, so that this phi developed across this one is directly proportional to the current which is flowing in the coil number A. If you remove this proportionality sign, so that this phi is equals to a constant n into I, where this constant is dependent upon the geometric properties of the coils. I call this as equation 1. Now, as there is a change in the current, you will find the induced EMF is also changing. The magnetic flux which is linked with the second coil is also changing. So that this is given by the Lenz's law. E is equal to minus of, that is, n d phi by dt. This is minus of d phi by dt. If we keep this value of phi from the equation number 1, so this E is equal to minus of d by dt into mi. So this is equals to minus of n di by dt. This is equal to. Therefore, from this one, we take this n is equal to, that is minus e upon di by dt. Right? So this is the equation for the magnetic, the mutual induction M. Now, if suppose the current which is changing in the coil number A is 1 ampere per second, in such a way that it is 1 ampere per second. If suppose di by dt is equal to 1 ampere per second, so that we get this M is equal to E. That is the mutual inductance of the coil is equals to the induced EMF developed in the coil. Okay, and is measured in Henry. So that this equation, from this equation, M is equal to minus of E divided by di by dt, This is measured in Henry. Okay, so we define now 1 Henry again. That is the mutual induction. This is called as the coefficient of the mutual inductance. The coefficient of mutual induction N is 1 Henry if there is the EMF which is to be developed in the coil is 1 volt. Because of the rate of change of the current is 1 ampere per second. Okay, 1 ampere per second. So that this is 1 Henry. The mutual induction of a coil is 1 Henry if there is the induced EMF is to develop across the second coil is equals to 1 volt. When there is a change of the current in the coil, it is 1 ampere per second. So this is about the mutual induction.